Okay, I'm going to work through the practice final. Start with a multiple choice. First multiple choice question is about charging. It's about charging by conduction and charging by induction. So charging by conduction is when you contact a charged object with another object and they become like charged. And charging by induction is when you don't contact the charged object with another object and they become unlike charged. So charging by conduction, which produces like charges, will cause the objects to repel. And charging by induction, which causes unlike charges, will cause the objects to attract one another. And so the correct answer here is that charging by contact will cause objects to repel. Charging by induction will cause objects to attract. So that's number one. Question number two. We're going to place two objects, two charges, two equal sized but opposite sign charges, either side of the origin on the x-axis, plus or minus 1 centimeter from the origin on the x-axis. So let me just draw a sketch of that. I'm going to draw the x-axis. Is the origin. I'm going to put one charge here, one charge over here. This is minus q, this is plus q. So the question asks us to comment on the resulting electrical field and electrical potential at the origin. Are they zero or non-zero? So maybe we'll start with the potential. The two charges make two potentials, and together they combine to make the resulting potential at the origin. So I could imagine writing that like so. Now, the potentials of the two charges are in proportion to the amount of charge. They have the same amount of charge in size in inverse proportion to the distance. They're at the same distances from the origin. But for the positive charge, the potential is going to be positive. For the negative charge, the potential is going to be negative. So you've got two equal and opposite potentials that will cancel out. So the overall potential at the origin is zero. What about the electrical field? Well, the total electrical field will be the sum of the two individual electrical fields of the two individual charges. But the electrical fields are vector quantities. So again, the electrical field strengths will be the same for the positive and negative charge because the quantity, the size of the charge is the same in both cases. The distance from the charge is the same in both cases. But in this particular case, the field lines or the field from the positive charge points away from the positive charge. The field lines or the field points towards the negative charge. And so the field of the positive charge will be directed towards the left. The field of the negative charge is also directed towards the left. And so these don't add up to be zero. And so the correct answer is that the field is non-zero, whereas the potential is zero. Okay, next question. We're asked to compare three capacitors, C1, C2, C3. They're drawn. We see their plate separations and their plate areas are in general different, and we're going to imagine placing equal quantities of charge on the plates of the capacitors. And we've got a comment on the electrical energies that are stored in the capacitors. And the way we're going to solve this is think about the relationship between the energy, the potential energy, and the charge in the capacitance. So the potential energy in a capacitor, sometimes we write it as P, sometimes you'll see it written as U, is 1/2 Q squared over C. Now, we're placing the same charge on all three capacitors. So the 1/2 Q squared is the same. But the capacitance of the capacitors is different. And because the potential energy is inversely proportional to capacitance, if you place the same charges on the capacitance, then the capacitor with the largest capacitance will store the smallest energy. The capacitor with the smallest capacitance will store the largest energy. So first, I'm just going to order the capacitances. The biggest capacitance is C2, and the smallest capacitance is C3. So C2 is biggest because capacitor goes up as the area of the plates goes up, and goes up as the separation between the plates goes up. So it's got big plates, small separation. Capacitor C3 is the smallest capacitance because it's got the smallest plate area and the largest plate separation. So this is the order of the capacitances, which means that the order of the energies will be that U3 with the small corresponding to the smallest capacitance will be the biggest stored energy. And U2 will be the smallest stored energy because that corresponds to the largest capacitance. So U3 has the biggest stored energy, then U1, the next biggest stored energy, and U2, the smallest stored energy. Question number 4. We got these two solenoids, and we're told the lengths of the solenoids are the same, the turns in the solenoid are the same, the currents in the solenoid are the same, but they've got different areas, different radii, different cross sections. And B has a larger radius, larger cross section than A. So we've got to compare the strengths of the fields in the two solenoids and the magnetic energies stored by the two solenoids. And we've got to say whether the fields are the same or different, whether the energies are the same or different. So let's start with the fields. So for a solenoid, the magnetic field is magnetic permeability times the number of turns per unit length times the current in the solenoid. And so in this case, since the number of turns, the length, and the current are all the same, the fields in these two solenoids are the same, so that we know the fields are the same. What about the energy? So the potential energy in the solenoid, in the inductors here, we can write that in terms of their inductance. It's 1/2 Li squared. And in turn, the inductance is mu naught n squared times the cross-sectional area A divided by the length. I've got to be a little bit careful here. So this L on the left here is the inductance of the solenoid. This L here is the length of the solenoid. Anyway, if we look at this equation for the potential energy, since the current is the same in the two solenoids, it's just going to be proportional to the inductance. And if we look at the equation for the inductance, we see it's proportional to the number of turns, that's the same. We see it's proportional to the length, that's the same. But we see it's also proportional to the cross-sectional area, and that's different. B's area is bigger, A's area is smaller. And so the fields are the same, but the energies are different. Okay, question number 5. Determine the direction of the magnetic force on an electron with a velocity v in a magnetic field B as shown below. So this is a right-hand rule problem. And I always have problems showing this on video, but I'm going to take my right hand and I'm going to point it up the page because that's the direction of the electron. Then I'm going to curl my fingers in the direction of the B field. That's towards the right. My thumb is pointing into the page. That would be the force on a positive charge. But the electron's a negative charge. And so the electron experiences a force that's out of the page. And so the answer, this guy here, out of the page by right-hand rule, remembering that the electron is a negatively charged particle. Okay, number 6. If the electric field in a light beam is doubled, so we're going to double the electrical field in a light beam, what happens to the magnetic field and what happens to the light's intensity? Well, we want to know the relationship between electric field, magnetic field, and intensity for this question. Well, first thing about light or other electromagnetic waves is that E and B are proportional to one another. So if we were to double E, we would double B. Second thing about light is that the intensity, the joules per second per square meter, that's proportional to the square of the electrical field or the square of the magnetic field. So it goes as the square of the fields. So if we're going to double the electrical field, we're also going to double the magnetic field. But if we double the electrical field, we're actually going to quadruple the intensity. And so the correct answer is that the magnetic field is doubled, the light intensity is quadrupled. Okay, question number 7. Question number 7 is about the two-slit experiment, or the two-slit setup, Young's two-slit setup. And in that experiment, in that setup, light passing through the two slits interferes with one another, and we get an interference pattern of constructive-destructive interference. And there was an equation that told you, that tells us, the location of the bright fringes of the interference pattern, the constructive fringes of the interference pattern on the screen in terms of several quantities. So one is the order of the fringe pattern, that's the integer m. Second one is the wavelength of the light, that's the lambda. And then the other two parameters are the slit separation and the screen distance. Those are the two geometrical parameters of the two-slit experiment. And so the equation tells you that if you were to increase D, so if we increase the slit separation D, we would actually decrease Y, the distance between fringes. And so increasing the slit separation decreases the separation between the fringes. Question 8. Okay, so we're asked to think about a trip of an astronaut from Earth to Vega at some very close fraction, 99% of the speed of light. And we're asked to think about whether the astronaut is measuring the proper time and the proper distance for the trip, whether the person on Earth, the spouse, say, is measuring the proper time, proper distance. Well, let me give you the answer first. So the astronaut measures the proper time. And the person on Earth, spouse, measures the proper distance. So why is that? Well, the reason that the person on Earth measures the proper distance is like the reason that a person sitting with an at-rest meter stick would measure the proper length of the meter stick. The meter stick is at rest in that person's reference frame. And Vega and Earth are at rest in the spouse's reference frame. So the spouse measures the proper distance. It's like the spouse measures the distance, the proper distance of a meter stick at rest in their reference frame. Now, what about the time? Who measures the proper time? The astronaut measures the proper time. You measure the proper time between 2 ticks of a clock, or the length of the trip, if the ticks of the clock occur at the same location, if the clock is at rest in your reference frame, if the beginning and end of the trip are at rest at the same place in your reference frame. And it's the astronaut. For the astronaut, the departure and the arrival from Earth on Vega are at the same place in the astronaut's reference frame. So the astronaut measures the proper time. And so that's a very important point about understanding the trip of the astronaut to Vega, is that the astronaut's going to measure the proper time, but the spouse is going to measure the proper distance. Okay, question 9, photoelectric effect. So photoelectric effect, if you remember, is when you shine light on a metal, you can liberate electrons from the metal. Electrons will be emitted from the metal. And the equation describing that effect is the following. So the kinetic energy of the liberated electrons is related to the frequency of the light, F is the frequency of the light, and the work function of the metal. Phi is the work function of the metal. And so this is the equation that describes the photoelectric effect. And the way I think of it is the incoming photons of light bring in energy. Some of that energy is consumed by the metal to release the electron, and the remainder the electron has as kinetic energy when it's liberated. So in this picture, this understanding of photoelectric effect, increasing the intensity of light doesn't change the energy of the emitted electrons. So it might create more emitted electrons, but it doesn't change the energy of the electrons. Rather, increasing the frequency of the light, F, increases the kinetic energy of the electrons. And so the correct answer here is that increasing the frequency increases the energy of the electrons. Okay, question number 10. Question number 10 we're asked about the Bohr model of the hydrogen atom. Remember, this is the model that incorporates both particle-like and wave-like features of the electrons that make up a hydrogen atom, or the electron that makes up a hydrogen atom. So in the Bohr model, based on that wave-particle duality, we came up with an expression for the energy, the binding energy, this expression here, and we came up with an expression for the angular momentum of the electrons, and it was this expression here. And the energy and the angular momentum are labeled with an n, and that n, that integer, is called a quantum number, and it labels the allowed orbits, labels the energy and the angular momentum of the allowed orbits. And so in the Bohr model of the atom with wave-particle duality, you can only have orbits that have certain energies, certain orbital angular momentum. And so the correct answer is that both the binding energy and the angular momentum are quantized. Okay, question number 11. In question number 11, we're told we've got a charge and it's floating in free space. We're told that the mass of the object that's charged is 1.5 kilograms. And we're told that it's floating in a field of 1,000 newtons per coulomb. And we got to figure out the magnitude of the charge on this object that's floating in free space. So what's going on here? What's going on here is we've got a charge. Here's the charge. And it's got some mass. And so there's a gravitational pull downwards, mg. I just think of that as the strength downwards. And there must be a corresponding electrical force upwards. And that electrical force in terms of the electrical field is QE. And for the charge to float in free space, it must be that the sizes of these two forces are equal, their directions are opposite. But this tells us that the charge must be equal to mg over E. And we're told the mass in the problem, we're told the electrical field in the problem, we know the acceleration of gravity. So we just plug in these three numbers. And I've already worked this out. When I plugged in the three numbers, I got 14.7 millicoulombs. 14.7 times 10 to the minus 3 coulombs. Okay, question number 12. An electron undergoes circular motion in a perpendicular 1.5 Tesla field. Calculate the angular velocity, omega, in units of gigahertz. That's 10 to the 9 inverse seconds. Okay, so when you have an electron in a uniform magnetic field, it will execute circular motion. And we figured out in class the relationship between the speed it orbits in a circle and the radius of the circle. And I'm going to write that equation down. I'm going to use this as my starting point. Now, this equation comes from equating the magnetic force with the centrifugal force. But let's just start with this equation. V is the speed, R is the radius of the orbit. And then Q and M are the properties of the charge. The mass of the charge of the charge. And B is the field that it's immersed in. If we divide through by R, that is actually the angular frequency, the radians per second, obtained by dividing the linear speed, meters per second, by the radius. And so the angular frequency is simply the charge to mass ratio for the particle multiplied by the B field. Now, we know the B field. We know the particle's an electron, so we know its charge and know its mass. And so all I've got to do is fill in those quantities. So I filled in the field was 1.5 Tesla. I filled in the charge was 1.6 times 10 to the minus 19 coulombs. I filled in the mass was 9.1 times 10 to the minus 31 kilograms. I plugged in all those numbers, and I'm going to write them all out. And I got 294 times 10 to the 9 hertz, or 294 gigahertz was my answer. Okay, next question. Next question is number 13. And in number 13, we've told that we've got a closed surface, and inside that closed surface are 3 positive charges of 1 nanocoulomb and 2 negative charges of -1 nanocoulomb. And we've got to figure out the total flux that emerges through that closed surface. So the total flux through a closed surface is related to the charge inside the closed surface by this little equation here. The sum of the charges divided by permittivity of free space. Okay, so in this case, our total charge is going to be just 1 nanocoulomb. And the permittivity of free space is 8.8 times 10 to the minus 12. The simplest way to write the units is farads over meters. And if you divide one by the other here, I've already calculated this, I got a flux that is 113 Newton meter squared per coulomb. The units of flux are newtons per coulomb, the units of field times area, because it's a field times an area. Okay, question 14. We're told we have a 1, 2, and a 3 ohm resistor, and we've got to calculate the circuit, find the resistance of the circuit that gives the lowest resistance. So that would be a parallel circuit. To make the lowest resistance, you build a parallel circuit of the 3 resistors. Because when you put resistors in parallel and you give the current multiple paths, then you lower the resistance. So this is the arrangement: 1 ohm, 2 ohm, 3 ohms. And so we just got to find out the equivalent resistance of this circuit. 1 over that equivalent resistance would be the sum of 1 over the 1 ohm resistor plus 1 over the 2 ohm resistor plus 1 over the 3 ohm resistor. Okay, so the equivalent resistance is 1 plus a half plus a third. So let's make a common denominator. So 6 would be a common denominator. So that's 6 over 6 plus 3 over 6 plus 2 over 6, which is 11 over 6. And so the equivalent resistance is going to be 6 over 11 ohms. Okay, question number 15. In question number 15, we've got a long straight current carrying wire. In the neighborhood of the wire, 1 centimeter from the wire, the field is 50 microtesla. And we've got to figure out the current that's flowing in that wire. Well, a starting point for this one is going to be the equation for the magnetic field of a current carrying straight wire. And that's this equation here. The field is equal to mu naught times the current in the wire divided by 2 pi r. R is the distance, the radial distance from the wire. Now, in this particular case, we want to find the current, and we know the field. So I'm just going to turn this equation around as an equation for the field. It's this equation here. And if you look at the right-hand side, we know the distance r is 0.01 meters. We know the field is 50 times 10 to the minus 6 teslas. We know mu naught is 4 pi times 10 to the minus 7. And so you can plug in all those numbers. I'm not going to write them all out. And when I plugged in all those numbers, I got a current that was 2.5 amps. Okay, question 16. Calculate the magnitude of the force per unit length between two current carrying wires, two long straight current carrying wires that are parallel to one another. So this is an arrangement where you've got a, let me just draw it. Here's a wire, here's a wire. They're both carrying currents. In this case, they're the same currents. They're separated by some distance. Let's call it D. And we've got to figure out the force between these two current carrying wires. The force per unit length, the force per meter is what the question asks for. Well, the force per unit length, force over length, is mu naught times the product of the two currents, so in this case it's just I squared, divided by 2 pi times the distance between the two current carrying wires. And look, we know the current, we know the distance, we know mu naught, and so all I have to do is plug in the 30 amps, square it, plug in the 0.005 meters, and we're going to get the force per unit length. Again, I'm not going to write all the numbers in, but I got 0.036 newtons for that force. Okay, question number 17. This is a question about interference with a soap bubble. So we're told that light is shone on a soap bubble and that the refractive index of the soap bubble is 1.33, it's water, and that the thickness of the soap bubble is 95 nanometers. And we've got to calculate the wavelength of light that's strongly reflected, constructive interference, for the m equals 0, the order 0 reflection. And so let's go ahead and do that. In that case, let me write down the general equation. For strong reflection from a soap bubble. The general equation is that twice the thickness of the soap bubble, so that's 2t, twice the thickness of the soap bubble is going to be m plus a half times the wavelength of the light in the soap bubble, which is the wavelength of the light in air, lambda, divided by n. Now, in our particular case, this is 0. We're thinking about the 0th order constructive interference. And so in this particular case, if I turn the equation around for the wavelength in air of this light is going to be reflected strongly is going to be equal to, let's see, 4nt. And we know n is 1.33. We know t is 95 nanometers. I just got to plug them in and multiply by 4. And if I do that, I got 505 nanometers. And so that's the wavelength of light that's strongly reflected. Okay, number 18 is the next one. An upright image 2 centimeters high is reflected by a curved mirror and produces a, an upright image of a 2.5 centimeter object is reflected by a curved mirror, and that image is 5 centimeters tall. And we got to figure out the image distance, including the sign, if the object distance is 1.2 centimeters. There's 2 pieces of information we're really being told here. So that's the important point. Firstly, we're being told the magnification. The image is 5 centimeters tall. The object was 2 centimeters tall. So the magnification is 2.5. And secondly, we're being told the object distance. So that's p, and the object distance is plus 1.2 centimeters. So it's told both these pieces of information. The magnification is positive because the image was upright. Well, we're asked to figure the image distance, and we can use the magnification equation to solve for that. Magnification equation says the magnification is minus q over p. Well, we want q, and so I can just multiply by p and multiply by minus 1, and I get an equation for q. And if I plug in the magnification of 2.5, the object distance of 1.2 centimeters, I'm going to get 3 centimeters minus 3 centimeters. And so that's the image location. Question number 19. So question number 19 says, sunlight has an intensity of 1400 watts per square meter. Calculate the radiation pressure on a reflective surface in micronewtons per square meter. Now, radiation pressure is the force per square area on the surface, and intensity is the energy per square area on the surface. And those 2 things are related to one another. And the relationship between them, if the surface is reflective, is the following. The radiation pressure, we call it P, the pressure, is the intensity over 2 times the speed of light. That's for a reflective surface. And so all we have to do is fill in the intensity, 1400 watts per square meter, fill in the speed of light, 3 times 10 to the 8 meters per second, and divide one by the other. And if you carry out that calculation, I'm again not going to put all the numbers in, I got 9.3 micronewtons per square meter. So that's the radiation pressure corresponding to this intensity. Okay, next question. Next question is number 20. And we're told that an electron has a momentum with magnitude 3 times its classical momentum. And we've got to calculate the speed of the electron. So if you remember, the classical momentum is mv. The relativistic momentum is gamma mv. The only difference is the gamma. So if the relativistic momentum is 3 times the classical momentum, is telling you that gamma equals 3. Now, gamma is related to the speed. So gamma is 1 over the square root of 1 minus v squared over c squared. Or if you rearrange that, the speed, v over c, is related to gamma. The speed v over c is 1 minus 1 over gamma squared. And so we can calculate the speed in units of c by just plugging in the gamma of 3. So the square root of 1 minus 1/9, which is the square root of 8/9. And the square root of 8/9 is 0.94. So the speed of the electron is 94% of the speed of light, 0.94 c. Okay, number 21. Number 21 says, what is the surface temperature in Kelvin of a star which radiates at a peak wavelength 970 nanometers? This is a case of the Wien law, which relates the temperature of a black body to the peak wavelength of the black body. And that law, let me write it down, is that the wavelength, the peak wavelength times the temperature is actually a constant. And that constant is 2.9 times 10 to the minus 3 Kelvin meters. And so if we know the peak wavelength, we can rearrange this for the temperature. The temperature will be 2.9 times 10 to the minus 3 Kelvin meters divided by 970 nanometers. That's 9.7 times 10 to the minus 7 meters. And if I divide one by the other, I get a temperature. The meters are going to cancel out. The meters are going to cancel out. And I'm going to be left with a temperature that I got 2,990 Kelvin. Okay, last numerical answer question, I believe. Okay, in number 22, we're told that the work function of lead is 4.14 electron volts. We got to find the cutoff wavelength in lead. Well, the cutoff, when you no longer get electrons emitted from the metal, is when the work function, phi, is exactly equal to the photon energies, which is Planck's constant times their frequency. Or if you write their frequency in terms of their wavelength, it's this equation here. So this equation relates the work function to the cutoff wavelength or the cutoff frequency. And so we can rearrange this equation. We want the cutoff wavelength in terms of an expression involving the work function. And then you can just plug in Planck's constant. That's 6.6 times 10 to the minus 34 joules seconds. Speed of light, 3 times 10 to the 8 meters per second. And the work function. And the work function is 4.14 electron volts. You'll want to write that in joules by multiplying by 1.6 times 10 to the minus 19, which will convert the electron volts to joules. If you go ahead and do that, again, I'm not writing all the numbers down, I got 300 nanometers. That's a shorter wavelength, a higher frequency than visible light. So visible light won't emit electrons from lead, but ultraviolet light will. And so that's the answer to number 22.